The local void is pushing our galaxy away at 260 kilometers per second. That figure is a measurement, not a guess. 3 facts frame the mystery before you have even settled in. First, 2 astronomers named Brent Tully and Rick Fisher found this emptiness in 1987. Second, the flat sheet of galaxies that holds the Milky Way is crossing the void's edge at nearly 260 kilometers per second. Third, that outward drift is only one part of a much larger motion. Our galaxy travels at about 631 kilometers per second, relative to the oldest light in the universe. Here is the problem that stops astronomers cold. Empty space holds almost no matter. Gravity needs matter to pull on anything at all. So how can a region of near nothing move an entire galaxy? The answer is not a push. It is the absence of a pull. Emptiness on one side means weaker gravity on that side. The fuller regions on the other side win the contest. We drift away from the void because the void cannot hold on to us. The motion is real, and it leaves a measurable trail. Over the next 2 hours we follow that trail from 3 directions. We trace Tully's careful measurement of the void's boundary. We separate our galaxy's full motion into 3 distinct pulls, and we arrive at a second hidden emptiness found in 2017, named the Dipole Repeller. If quiet, evidence-driven space documentaries help you rest, consider subscribing to Gravity of Sleep. The story begins in 1987. In that year, Brent Tully and Rick Fisher were studying the galaxies near our own. They were charting where galaxies sit and how fast they move. Most of the sky was busy with structure. Then they noticed a gap. Beside our own group of galaxies lay a vast region that was nearly barren. Few galaxies filled it. Little light came from it. They named this quiet neighbor the local void. It was the first time anyone had marked this particular emptiness on a map, and it turned out to be sitting right on our doorstep. The name is plain, and that plainness is honest. A void in astronomy is not perfectly empty. It is a region where galaxies are unusually rare. Matter still threads through it in thin strands. But compared to the crowded regions around it, a void is a desert. The local void is the nearest of these deserts to us. Its edge sits close to the structure we live inside. That closeness is what makes it matter. A distant emptiness would barely touch us. This one is near enough to steer us. To see how, you have to know where our galaxy actually lives. The Milky Way rides on a broad, flat structure of galaxies. Astronomers call it the local sheet. It is thin in one direction and wide in the others, like a great pancake of galaxies. It reaches outward to roughly 7 megaparsecs. That is about 23 million light-years across. Our galaxy does not sit at the center of this sheet. It sits near one face of it, and that face looks directly out into the local void. We are parked on the shore of the emptiness. Now comes the number that names this episode. When Tully and his colleagues studied the motions along the local sheet, they found something sharp. At a distance of about 7 megaparsecs, the pattern of galaxy velocities changes suddenly. This is called a velocity discontinuity. On one side, galaxies move one way. On the other side, the motion breaks. The measured result placed the local sheet in flight from the void center at nearly 260 kilometers per second. That is the outward drift. That is the sound of the void emptying itself, with us carried along on the tide. The size of the local void is hard to pin down, and the honesty of that difficulty matters. From the original measurements, the void spans at least 45 megaparsecs. That is roughly 150 million light-years from side to side. But the astronomers added a careful warning. To whatever degree the void is not truly empty, it must be even larger than that. The emptier it appears, the smaller it seems. The more faint galaxies hide inside it, the wider its real reach. So 45 megaparsecs is a floor, not a ceiling. The true desert may run larger still. The center of that desert lies far from us. The distance from our position to the middle of the local void is at least 23 megaparsecs. In more familiar units, That is about 75 million light-years away. Think about what that means. We are not being nudged by something next door. We are responding to the shape of a region tens of millions of light-years across. The push, if we can call it that, is spread across an enormous volume of near nothing, and still it registers as a clean, steady drift in our measured motion. The void is not featureless. Thin filaments of galaxies stretch across it like cobwebs across a dark room. These wispy strands divide the emptiness into sectors. Astronomers describe a near part, a northern part, and a southern part. The filaments are the last threads of structure inside a region that is otherwise draining. They mark the walls between separate pockets of desert, and they hint at what a void really is. It is not a hole cut into the universe. It is a place where matter has slowly left, flowing outward toward the crowded regions that surround it. Sit with the strangeness of that for a moment. Everything we can see is being drawn toward mass. Galaxies fall toward clusters. Clusters gather along filaments. And yet part of our own motion points the other way. Part of it points away from the emptiness at our back. The void does not reach out and shove us. It simply fails to pull us back. Every other direction tugs a little harder than the void's direction does. The net result is a galaxy sliding steadily away from the quiet. Nothing is chasing us. Something is merely failing to hold us in place. That raises a hard question. How do you measure the motion of something you are sitting inside? We cannot step outside the Milky Way to watch it move. We cannot plant a flag in empty space and clock our speed against it. Instead, astronomers measure motion against distant reference points. They measure it against other galaxies. They measure it against the faint background glow left over from the early universe. Peculiar motion is the name for movement that cannot be explained by the smooth expansion of space alone. It is the extra drift, the part that reveals the pull and the absence of pull around us. When that extra drift is fully measured, it comes to about 631 kilometers per second, give or take 20. In plain terms, our galaxy is moving through the cosmos at roughly 1.4 million miles per hour. That is the total. And the total is what the rest of this journey must explain. The 260 kilometers per second from the local void is only one piece of it. Something else is adding the rest. To find those other pieces, the astronomers had to break the single number apart. They had to ask which direction each part of our motion truly points toward. The answer would come from patient surveys of galaxy distances and speeds. It would take Tully and a wider team years of work to sort the motion into its parts. One part is the push from the emptiness behind us. Another part is a pull from a great cluster of galaxies ahead of us. And a third part is a deeper pull still, from structures far larger and far more distant. Each part is a vector, an arrow with a size and a direction. Added together, those arrows make the single arrow of our true motion. Separated, they tell the story of everything tugging on our galaxy at once. That separation is where we go next. Consider first the arrow that points ahead of us. It leads toward the constellation of Virgo and toward a great swarm of galaxies gathered there. That swarm is the Virgo cluster. It sits about 17 megaparsecs away, a dense knot of hundreds of galaxies bound together by their own gravity. Virgo is the nearest large cluster to us. It is heavy enough to be felt across that vast gulf, and it is pulling. Our galaxy, and the whole local sheet with it, drifts toward Virgo at roughly 185 kilometers per second. That is the second piece of our motion. It is a true pull, a falling toward mass. Where the void behind us empties, Virgo ahead of us gathers. So one part of our journey is a departure, and another part is an approach. The two are not opposites in the sky. They lie in different directions, and their arrows only partly overlap. Now hold both of those arrows in mind. The push from the emptiness measures about 260 kilometers per second. The pull toward Virgo measures about 185. Together they still do not reach the full speed at which we travel. A third arrow is needed, and it is the largest of the three. This last component points toward far more distant structure. It runs in the direction of the Centaurus and Hydra regions of the sky. It reaches toward mass on a scale that dwarfs Virgo. This deep attraction contributes roughly 455 kilometers per second to our motion. It is the strongest single term in the sum, and it comes from the most remote source of the three. So there are three arrows. One pushes at about 260, one pulls at about 185, one pulls harder still at about 455. Each has its own size, each has its own heading across the sky. None of them points the same way as the others. To add them, the astronomers could not simply stack the numbers. They had to add them as vectors, respecting direction as well as strength. Two arrows that point in nearly opposite directions partly cancel. Two arrows that point nearly the same way reinforce. When Tully and his colleagues laid the three arrows head to tail, they folded into a single resultant. That single arrow is the true velocity of the local group through space, and its length is the number the microwave background had already revealed. That number is 631 kilometers per second, give or take about 20. It is the speed of our whole galaxy, relative to the ancient light of the early universe. Translate it into more familiar units, and it becomes almost absurd. It is close to 1.4 million miles per hour. There is no way to feel it. Every atom in your body carries it equally, so nothing inside us resists it. The Earth, the Sun, the entire Milky Way, and our small companion galaxies all share this drift. We are riding it now, quietly, as we always have. And what the decomposition shows is that this single grand motion is not the work of one cause. It is a negotiated result. Three influences, at three scales, argue at once. The final speed is what they agree upon. This is the deeper reward of breaking the number apart. A single measured velocity tells you that you are moving. It does not tell you why. By separating the motion into components, the astronomers turned a fact into an explanation. They could say that this much of our speed comes from the void draining behind us. This much comes from Virgo gathering ahead of us. And this much comes from something vast and distant beyond them both. The void, remarkably, is not a minor footnote in this accounting. Its 260 kilometers per second is a substantial share of the whole. An emptiness earns its place beside a cluster of hundreds of galaxies. That is the strange balance this survey uncovered, but a difficulty hides inside that sentence. We keep saying the void pushes. Emptiness has no matter to push with. A region with fewer galaxies has less gravity, not some new outward force. So how can nothing shove a galaxy? The answer is that the push is not really a push. It is a comparison. Gravity is always an attraction, always a pull toward mass. What matters for any galaxy is not one pull, but the sum of every pull acting on it at once. A galaxy sitting near the edge of the local void feels denser regions on one side. It feels the emptiness on the other. The dense side pulls hard, the empty side pulls weakly. The two pulls do not cancel. The result is a net drift away from the emptiness and toward the mass. From the outside, this looks exactly like being pushed by the void. The galaxy moves as if something behind it was shoving it forward. In truth, it is simply falling toward whatever lies ahead, while nothing much holds it back from behind. Underdense regions therefore behave, in the mathematics of motion, as if they repelled. Physicists sometimes describe this by imagining a fictitious source of anti-gravity sitting at the center of the void. That fiction is a bookkeeping trick. It captures the real effect without claiming a real force. The void is a place where the usual restraining pull is missing. An absence, when everything around it pulls, mimics rejection. There is a simple way to test whether the numbers even make sense. Imagine a perfectly round void carved into an otherwise smooth universe. Matter inside such a region would flow outward as the emptiness grew. A basic model predicts how fast. It gives an evacuation rate of about 16 kilometers per second for every megaparsec of the void's radius. That is a rule of thumb, not a precise law. Yet it lets us check the observation against expectation. Our measured outflow is about 260 kilometers per second. Divide that by 16, and you need a void radius of well over a dozen megaparsecs. The local void is inferred to be at least 45 megaparsecs across. Its radius alone is large enough to drive the motion we see. The simple picture and the real measurement agree. That agreement is quietly important. It means the 260 kilometers per second is not a fluke of some exotic physics. It follows from the ordinary rules of gravity acting on an ordinary emptiness. A void that big, evacuating at that rate, should push its neighbors at roughly the speed we observe. The theory does not explain everything. It leaves the exact shape of the void uncertain, and voids are never perfect spheres. Wispy filaments of galaxies cross the local void and break its symmetry. But the order of magnitude is right. And in cosmology, matching the order of magnitude with a clean physical argument is often the first sign that a discovery is real. Still, a question lingers at the edge of all this. The three arrows explain our local motion well, yet the largest of them, the 455 kilometers per second, points into the deep distance. It gestures toward mass we can name in part, but not fully weigh. For decades, astronomers spoke of a great attractor in that direction, a concentration of galaxies pulling the whole region toward it. Beyond it lay an even richer concentration, farther still. The pull seemed to come from what was there, from the crowded, massive places in the sky. That felt complete. Overdensities attract, and we fall toward them. The account appeared to close, but the void had already taught the astronomers a lesson. Emptiness matters as much as abundance. If a void behind us can add hundreds of kilometers per second to our motion on nearby scales, what might a far larger emptiness do on grander scales? The map of attractors was only half the picture. Somewhere on the opposite side of the sky, opposite the crowded regions we were falling toward, there might be another great emptiness. Not a small local one, but a vast underdense expanse pushing the entire flow of galaxies from behind. No survey had yet drawn it. The idea was there, waiting, implied by the same logic that explained our 260 kilometers per second. It would take another decade and a far larger dataset to find it. The astronomers would need not the motions of the few dozen galaxies nearest us, but the motions of thousands, spread across a great volume of space. They would need to reconstruct not just where galaxies are, but where their velocities point, and to trace those flows back to their sources. When they did, in 2017, they would map a structure no telescope can see directly. It has almost no galaxies to shine. It reveals itself only through the way everything around it moves. And it would extend the story of the local void to a scale that reaches across a substantial fraction of the observable cosmos. That structure has a name now. Before we reach it, we should return to the beginning, to the first faint sign that an emptiness sat beside us at all. In 1987, two astronomers looked at the sky beside our galaxy and noticed something that was not there. Their names were Brent Tully and Rick Fisher. They were not hunting for an emptiness. Emptiness is not the kind of thing a telescope is built to find. A telescope collects light, and empty space sends none. What Tully and Fisher were doing was more ordinary and more patient. They were cataloguing galaxies. They were measuring where nearby galaxies sat and how they clustered into sheets and filaments. And in the course of that careful accounting, a gap opened in the map. The gap sat close to us, in a particular direction on the sky. In that direction, the galaxies simply thinned and stopped. Around it, the cosmos behaved as expected. Galaxies gathered along bright threads. They pooled into groups. They traced the familiar lacework that fills the nearby universe. But in this one region, the lacework fell away into almost nothing. Tully and Fisher gave the region a plain and honest name. They called it the local void. The word local matters here. This is not some distant curiosity glimpsed at the edge of what we can see. It begins near our own front step. To understand why this discovery was so difficult, consider what it means to measure nothing. A void does not announce itself. It has no center that glows. It has no surface that reflects. The only way to know it is present is to notice the shape of everything around it. You map the galaxies you can see, and then you study the hole they leave behind. The void is defined entirely by its absence. It is the missing piece in a puzzle you must first assemble from millions of separate points of light, and because it produces no signal of its own, it is easy to miss and easy to doubt. For years, the local void remained exactly that kind of quiet finding. It was a region on a map where the galaxies had grown scarce. Astronomers knew it was there, they could sketch its rough edges. But knowing that a void exists is different from understanding what it does. A hole in a map is a static thing. It sits still. The deeper question was whether this particular emptiness had any effect on the galaxies at its border. Was it merely a place where nothing happened to be, or was it actively shaping the motion of its neighbours? Answering that would require more than a census of positions. It would require the far harder measurement of motion. That measurement is the heart of the story, and it took 2 decades to complete. The reason is subtle. Every galaxy in the nearby universe is carried outward by the general expansion of space. That expansion is smooth and predictable. The farther a galaxy lies, the faster it recedes. If every galaxy obeyed that rule perfectly, there would be nothing to explain. But galaxies do not obey it perfectly. Each one also drifts a little on its own, pushed and pulled by the gravity of the structures around it. That extra drift is called a peculiar motion. It is the private velocity of a galaxy, laid over the public velocity of the expansion. To find the local void's effect, astronomers had to separate these 2 motions. They had to measure how fast a galaxy appears to move, and then subtract the part that comes from cosmic expansion. Whatever remained was the peculiar motion, the true fingerprint of gravity at work. This is delicate arithmetic. It demands that you know a galaxy's distance with real precision, because the expansion velocity depends on distance. Get the distance wrong, and you assign the leftover motion to the wrong cause. For nearby galaxies, the distances are especially hard to pin down, because the expansion signal is small and easily swamped by local drift. By the middle of the 2000s, the tools had improved enough to try. Our Brent Tully returned to the void he had helped name, now armed with far better distances to the galaxies around it. He worked with a team of researchers who had spent years refining these measurements. Edward Shire, Igor Karachentsev, Helene Courtois, Dale Kachevsky, Luca Rizzi, and Alan Peel joined him in the effort. Their aim was direct. They wanted to know whether our own galaxy, and the flat sheet of galaxies it belongs to, felt the void beside it. In late 2007 they finished the work. The paper was accepted on the 3rd of December that year. It appeared in the Astrophysical Journal under a title that stated the finding plainly. Our peculiar motion away from the local void. The result was a number, and the number was sharp. At the boundary of our galactic neighborhood, roughly 7 megaparsecs from us, the team found a clean break in the velocities. Galaxies on our side of that boundary were moving together, as a body, away from the center of the void. The speed of that motion was about 260 kilometers per second. It was not a gentle statistical lean, it was a discontinuity, a step in the data, a place where the pattern of motion changed. On one side of the boundary the galaxies belonged to the outflow, on the other side they did not. That step is what turned a hole in the map into a force in the story. 7 megaparsecs is a distance worth holding in mind. It reaches out to the edge of the flattened structure of galaxies that contains us, the local sheet. Our galaxy is not floating alone. It sits within this broad, thin layer, and the whole layer moves as a unit. The 2007 measurement showed that this entire sheet is sliding away from the void's interior at that steady pace. We are not being nudged as individuals, we are riding a surface that is peeling away from an emptiness on one side. The value itself sits within a simple physical picture, and the picture gives it weight. In a smooth universe, a spherical region that is emptier than its surroundings will tend to expel whatever matter clings to its rim. The larger the empty region, the stronger that expulsion. A rough theoretical estimate puts the outflow at about 16 kilometers per second for every megaparsec of the void's radius. The local void is enormous, at least 45 megaparsecs across, which is about 150 million light-years. Feed a void of that scale into the simple relation, and the outflow it should produce lands close to the 260 kilometers per second that was actually measured. The number is not an accident, it is what a void of this size is expected to do. That agreement is quietly important. It means the measured motion and the mapped emptiness are telling the same story. The gap Tully and Fisher had drawn in 1987 was not just a scarcity of light, it was a scarcity of matter large enough to leave a gravitational mark on everything at its edge, including us. The 45 megaparsec figure is itself a floor, not a ceiling. The team was careful to note that to whatever degree the region is not perfectly empty, it must be even larger to hold the galaxies it does contain. And it is not seamless. Thin filaments of galaxies thread across it, dividing the interior into a near sector, a northern sector, and a southern one. The void is vast, ragged at its edges, and mostly dark. There is one more distance in this early chapter that anchors the rest. The center of the local void, the deepest part of the emptiness, must lie at least 23 megaparsecs from us. That is roughly 75 million light-years away. We are not near the middle of the void. We sit on its rim, on the crowded side, where the galaxies gather along the sheet. The void opens out beyond us, away from the denser cosmos, and it is that opening we are steadily backing away from. The geometry is almost intuitive once stated. Matter drains from the empty toward the full, and we are being carried along on the tide of that drainage. Now the picture begins to sharpen, and with it a puzzle. 260 kilometers per second is a real and substantial speed, yet it is not the whole of our galaxy's motion through the cosmos. When astronomers measure how fast the local group is traveling against the faint background glow of the early universe, the cosmic microwave background, they find a far larger figure. The local group is moving at about 631 kilometers per second relative to that background, give or take 20. In more familiar units, that is close to 1.4 million miles per hour. The void's outflow of 260 kilometers per second is a major share of that motion. But it is plainly not all of it. Something else is pulling us as well. This is where the story stops being about a single emptiness and becomes about a balance of forces. Our galaxy's total motion is a sum. It is the outcome of everything in the universe tugging on us at once, near and far, dense and empty. The void behind us contributes one piece. But there are structures ahead of us, rich with galaxies, whose gravity draws us forward. To make sense of the full 631 kilometers per second, the 2007 team did not stop at the void. They took our total motion apart and tried to name each contribution to it. And when they laid the pieces side by side, the void turned out to be one voice in a larger conversation. A conversation between the things that push and the things that pull, all of them acting on us at the same moment across tens of millions of light years. Consider what that decomposition actually asks of us. Our galaxy has one motion. It travels in a single direction at a single speed, yet that one motion hides several separate causes underneath it. The team wanted to know how much each cause contributed, so they built a model of the nearby universe as a field of gravity. Every known concentration of galaxies became a source of pull. Every measured emptiness became a place where pull was missing. Then they asked a simple question. Which combination of these forces would reproduce the motion we actually observe? The first piece was the void itself. The evacuation of the local void accounts for roughly 259 kilometers per second of our speed. That is the push we have been tracing all along. It arrives from behind us. It comes from the emptiness we are steadily draining out of. On its own, it is already one of the largest single contributions to our journey through the cosmos. The second piece points in a very different direction. It points toward the Virgo cluster. Virgo is a dense swarm of galaxies about 17 megaparsecs away from us. It is the nearest great gathering of galaxies to the local group. Its combined gravity reaches across that distance and draws us toward it. In the 2007 analysis, that pull contributes about 185 kilometers per second. It is a genuine tug, but it is not the strongest one. The third piece is larger still. It points beyond Virgo, toward the general direction of Centaurus and Hydra. There, on scales far greater than our immediate neighborhood, sit concentrations of mass so vast that their influence dominates the sum. That larger attraction contributes around 455 kilometers per second. It is the single biggest term in the whole calculation. It reminds us that our motion is not set only by what is close. It is set, in large part, by structures tens of millions of light years away. Now add the pieces together. The push from the void, the pull from Virgo, the far pull towards Centaurus and beyond. They do not point along the same line, so they do not simply stack into one number. They combine as vectors, each with its own direction. When the team resolved them into a single resultant, the answer matched the measurement. Our total peculiar motion came out near 631 kilometers per second, relative to the cosmic microwave background. That figure carries an uncertainty of about 20 kilometers per second either way. It is not a guess. It is one of the best measured motions in all of cosmology. 631 kilometers per second is a difficult speed to feel, so render it in more familiar terms just once. It is roughly 1.4 million miles per hour. It is close to 2.25 million kilometers per hour. And here is the strange part. We do not feel any of it. There is no wind, no shudder, no sense of speed. The Earth carries us. The Sun carries the Earth. The galaxy carries the Sun. And the galaxy itself is being carried, silently, at more than 600 kilometers every second, through a universe whose structure we are only beginning to map. What the decomposition revealed was a kind of accounting. Our motion is not a mystery with a single answer. It is a ledger. The void writes one entry. Virgo writes another. The distant mass beyond writes the largest of all. And the void's entry, that push of about 260 kilometers per second, is not a rounding error. It is a leading term. It stands beside the great attractors of the local universe as an equal partner in setting our course. But a question has been waiting patiently beneath all of this. It is the question a careful listener asks the moment the word push appears. How can an emptiness push anything at all? A void is defined by what it lacks. It is a region drained of galaxies, thinned of gas, poorer in matter than the space around it. It has less gravity, not more. It should be the weakest thing in the sky. So how does it drive our galaxy away at hundreds of kilometers per second? The answer is that the void does not push in any ordinary sense. Nothing reaches out from the emptiness to shove us. The word push is a description of the result, not the cause. What is really happening is a matter of balance. Gravity pulls in every direction at once. On one side of our galaxy sits a region rich with mass. On the other side sits the void, poor in mass. The rich side pulls us hard. The empty side pulls us only weakly. The forces do not cancel. There is a difference between them. And that difference has a direction. It points away from the emptiness and toward the density. Think of it as a competition that the void is destined to lose. Every scrap of matter around us tries to draw us toward itself. The full regions win that competition because they have more to offer. The empty region loses it because it has almost nothing. And a losing pull, set against a winning pull, feels exactly like a push in the opposite direction. We drift away from the void not because it repels us, but because everything else outpulls it. The emptiness is simply the direction in which the least gravity lies. This reframing matters, because it turns a paradox into a mechanism. There is nothing mystical about a void that moves galaxies. It is the plain arithmetic of gravity, applied to an uneven universe. Where matter is clumped, motion follows the clumps. Where matter is missing, motion flees the gap. Our galaxy sits on the edge of one of the largest gaps in our part of the cosmos. So our galaxy flees it, steadily, in the direction the model predicts. The physics can even be made quantitative in a simple case. Imagine a perfectly spherical void carved out of an otherwise smooth universe. As that sphere empties, the matter inside it flows outward toward the walls. A basic model gives the rate of that outward flow. It grows at roughly 16 kilometers per second for every megaparsec of the void's radius. The larger the void, the faster the material at its edge streams away. This is a rough rule, not an exact law of nature. Real voids are not perfect spheres, and the universe around them is not perfectly smooth. But the rule gives us a way to check the story for consistency. So apply it. The local void is inferred to be at least 45 megaparsecs across. That is something like 150 million light-years from one side to the other. A void of that scale, expanding by that simple rule, would drive material at its boundary outward at a speed close to the 260 kilometers per second we actually measure. The numbers line up. A void of the size we see, behaving as a draining sphere should behave, produces a push of about the strength we feel. The theory and the observation shake hands. That agreement is quietly powerful. It means the 260 kilometers per second is not an isolated fact that happens to sit in our data. It is what a void of this size ought to produce. The measurement and the mechanism support each other. The emptiness is large enough and empty enough to explain the motion it is blamed for. We are not merely drifting away from nothing. We are drifting away from a specific nothing, of a specific scale, at the specific speed that scale demands. And yet the picture still has an edge of humility built into it. The phrase used to describe the void's size is at least 45 megaparsecs. At least. The truth may be larger. To the degree the void is not perfectly empty, and no real void ever is, it must in fact be bigger than the simplest reading suggests. Our own distance to its center is quoted the same cautious way. At least 23 megaparsecs, at least 75 million light-years to the middle of the emptiness we ride the rim of. These are floors, not ceilings. The real dimensions push outward from them, into territory we have not fully mapped. So we arrive at a curious kind of understanding. We know our galaxy is being driven away from the local void. We know the speed. We know how a region of nothing can produce that speed without ever reaching out to touch us. We know the void is large enough to make the numbers work. But we do not yet know exactly how large it is, or exactly where its heart lies. The mechanism is clear. The measurement is precise. The object doing the pushing remains, in its full extent, only roughly drawn. That gap between a sharp motion and a blurred source is what drives the next chapter of this story. If a nearby void can shape our path this strongly, then perhaps our push does not end at the walls of the local void. Perhaps the same logic scales upward. Perhaps there are far larger emptinesses, deeper and more distant, whose absence of gravity steers not just our galaxy, but whole rivers of galaxies flowing together across the sky. For years, the void behind us was treated as a local curiosity, a dent in our own backyard. Then a small team of researchers began to wonder whether the greatest emptiness of all was hiding much farther out, unseen, quietly repelling everything in our corner of the universe at once. And when they went looking for it, what they found reshaped the map. The search began with a simple frustration. Our galaxy moves at a known speed. It moves in a known direction, yet no single object in the sky fully explained that motion. The Great Attractor pulled from one side, the Shapley concentration pulled from farther still. Together they were strong, together they were not enough. Something in the accounting was missing, and it had been missing for decades. In the year 2017, 4 researchers set out to close that gap. Yehuda Hoffman worked at the Hebrew University of Jerusalem. Daniel Pomerada worked in France, at a research center near Paris. Brent Tully returned to the problem from the University of Hawaii, the same astronomer who had helped find the local void 30 years earlier. Helene Courtois worked at the University of Lyon, They published their result in the journal Nature Astronomy. They gave it a plain and striking name. They called it the Dipole Repeller. Their method inverted the usual habit of astronomy. For centuries, sky mappers had counted what was there: bright galaxies, dense clusters, glowing walls of matter. This team decided to map what was absent. They took the measured motions of thousands of galaxies. They reconstructed the flow those motions implied. Then they asked a careful question: where must matter be piled high to pull this flow forward? And where must matter be scarce to let it drift away? The answer arrived as a shape. On one side of the sky sat the Shapley concentration, an immense gathering of galaxy clusters, tugging everything toward it. On the opposite side, in almost perfect mirror, sat a vast and quiet emptiness. Nothing luminous marked it. No cluster announced it. It revealed itself only through the way galaxies fled from it. The team had found the largest known underdense region influencing our motion, and it worked against Shapley like the far end of a seesaw. This is why the name fit. A dipole has two poles. One pole attracts, one pole repels. The Shapley concentration was the attractor, the new emptiness was the repeller. And the paper made a claim that rearranged the old picture. The attractor and the repeller contribute roughly equally to our motion. The pull of distant matter is only half the story. The push of distant absence is the other half. For years the emptiness had been left out of the sum. Now it stood as an equal partner. The scale of the flow they traced is hard to hold in the mind. The team reported that the bulk motion of galaxies in our region extends outward to roughly 20,000 kilometers per second, measured in redshift. That figure is not a speed you can picture. It is a way of stating a distance. Translated into space, it reaches beyond 1 billion light years. That span is close to 1/10 of the radius of the observable universe. A single coherent current of galaxies, drifting together across 1/10 of everything we can see. Place the landmarks along that current and the geometry becomes clear. The Great Attractor sits about 150 million light years from the Milky Way. The Shapley concentration sits far beyond it, about 600 million light years away, in roughly the same direction. And the Dipole Repeller lies on the far side of the sky, in nearly the opposite direction from Shapley. We are caught between them, drawn toward the crowded pole, pushed from the empty one. Both hands press in the same overall sense, and our galaxy obeys. The exact address of the repeller is still lightly held. Later summaries place the mapped structure at roughly 220 megaparsecs from the Milky Way. They set it near a point in the sky at right ascension 22 hours 30 minutes, and a declination of about plus 37 degrees, sitting diametrically opposite the Shapley concentration. These coordinates are useful for orientation. They are not carved in stone. The repeller is defined by scarcity, and scarcity is difficult to pin to a precise center. What the data fixes firmly is the direction of the push. What remains softer is the exact distance to its heart. Notice how faithfully this larger discovery echoes the smaller one behind us. The local void repels us at short range through the same principle. Matter gathers on one side, matter thins on the other. A galaxy between them drifts away from the thin side. The Dipole Repeller is that principle written across 1,000 times the distance. The physics did not change when the scale grew. Only the size of the emptiness changed, and with it, the reach of its influence. That echo carried a quiet warning for astronomers. If one great void had hidden in plain sight for so long, others might be hiding too. The universe does not label its empty regions. They emit no light to catch a telescope. They can only be inferred from the way matter moves around them. So the same team, and others using the same approach, kept watching the flows for further asymmetries. Within the same year, a second candidate surfaced. Researchers described a distinct repelling underdensity in a different part of the sky, and some accounts named it the cold spot repeller. This second structure is reported with far less certainty than the Dipole Repeller. Its identity is preliminary. Its properties are debated. It should be held loosely, as a hint rather than a settled fact. But even as a hint, it points somewhere important. The sky may hold more than one great emptiness steering the local flow, and the map of what pushes us may still be incomplete. 2 years later, the story turned back toward home. In the year 2019, Tully's group at the University of Hawaii returned to the local void itself with a far richer dataset. They drew on a catalogue of galaxy distances built over many years. They analysed the motions of roughly 18,000 galaxies. Their goal was not another distant abstraction. It was a three-dimensional map of the boundary, where the local void meets the denser region around the Virgo cluster. They published the result in a leading astronomy journal in the summer of that year. The map gave shape to something that had been mostly a number. It showed our local group perched on the rim of the emptiness, with the crowded Virgo region on the far side. It let researchers watch, in reconstructed motion, how galaxies near that boundary are drawn one way and pushed the other. And it delivered a clean accounting of our own strange speed. Roughly half of the local group's deviation from smooth cosmic expansion, that motion of more than 600 kilometers per second, comes from a single combination. The pull of the Virgo cluster on one side, the continued expansion and emptying of the local void on the other. Two effects. One shared direction. Half of our anomalous motion explained by that pairing alone. This is the quiet power of the whole research program. It does not merely say that we move. It divides the motion into causes and assigns each a share. The local void supplies its portion through evacuation. Virgo supplies its portion through gravity. The larger structures beyond supply the rest. And when the shares are added, the sum matches the speed measured against the ancient light of the cosmic background. A messy total resolves into named parts. The three-dimensional map also made the emptiness feel less like a gap in a table and more like a place. It has a near edge, close to us. It has an interior we sit beside but do not occupy. It has a far wall, where the outflowing region gives way to the pull of denser neighbours. For the first time, the void behind our motion could be turned in the mind like an object, rather than recited as a figure. The abstraction had acquired a surface, yet the map did not close the case. It sharpened it. The clearer the boundary became, the more clearly one question stood out. How far does the emptiness truly extend? The near edge is well defined by the galaxies that trace it. The deep interior is defined by almost nothing, because almost nothing is there. Measuring the true size of a void means measuring the reach of a silence, and silence in astronomy is the hardest signal to bound. So the picture that emerged across these years is layered rather than simple. At the smallest scale, the local void presses on the local sheet at about 260 kilometers per second. At an intermediate scale, the Virgo cluster adds its pull, and together with the void's expansion it explains roughly half of our peculiar motion. At the largest scale, the Dipole Repeller and the Shapley concentrations set up a push and a pull that reach across more than 1 billion light years. Each layer uses the same law. Matter attracts. Emptiness, by comparison, lets go. And through every layer, the same team keeps appearing. Tully at the center of the first discovery, the precise measurement, and the later three-dimensional map. Courtois beside him on the largest structure. Hoffman and Pomerade supplying the technique that turned raw motions into visible flows. This is not the work of a single night or a single instrument. It is a slow assembly, carried out over 3 decades, each result feeding the next question. The local void that began as a curiosity in the year 1987 grew, discovery by discovery, into a doorway onto the emptiest and most influential regions of the nearby universe. There is a humility built into all of it. The velocity is known with real precision. The direction is firm. The mechanism is understood, and it is not mysterious once stated, but the objects doing the work are drawn only in outline. The local void's full extent is uncertain. The Dipole Repeller's exact center is uncertain. The second repeller may or may not be real. We stand inside a system we can measure far better than we can map. That imbalance is not a failure. It is the honest condition of studying things that shine by their absence, which returns us, once more, to the emptiness at our back and the motion it commands. The push is steady, the void is not finished. And a void that is still emptying is a force that is still at work on our future. Consider what still at work means once it is written in numbers. A simple model captures the idea cleanly. An empty spherical region in an otherwise even universe drives matter outward. The rate of that outward push grows with the size of the void. For every megaparsec of void radius, the outflow rises by roughly 16 kilometers per second. A void 45 megaparsecs across, or larger, would produce an outflow near 260 kilometers per second. That is very close to the number we actually measure. The theory and the observation reach out and touch. The local sheet leaves the void at nearly the speed the void's own emptiness predicts. That agreement is quiet, but it carries weight. It tells us the push is not a coincidence of a few nearby galaxies. It is a property of the geometry itself. The void has a size, and the size has a consequence. Matter drains from the hollow center toward the denser walls. Our galaxy rides one of those walls outward. The motion is not an accident of where we happen to sit. It is simply what the edge of a growing emptiness does, and the emptiness, by every expectation, is not done growing. Standard cosmology gives that growth a direction. Dense regions pull matter inward and grow denser still. Empty regions surrender their last stragglers and grow emptier. The local void is expected to keep expanding and draining over cosmic time. The few faint galaxies still inside it will continue falling toward the surrounding structure. As they leave, the void becomes even more hollow. A more hollow void produces an even cleaner outward push. So the force that carries us now is not fading. In the language of that simple model, it is a force that slowly strengthens as the space behind us empties. We should be careful about how far to follow that thought. The dossier lets us say the trend, not the destination. The void will keep emptying. Our galaxy will keep drifting away from it. But the exact future path of the Milky Way depends on more than one void. It depends on the full tug of war across the local universe. And that war has more than a single front. Return then to the accounting of our motion, because it is worth holding all three numbers in the mind at once. Our galaxy's total speed against the cosmic microwave background is 631 kilometers per second, give or take 20. That figure does not come from one source. It is the sum of separate pulls and pushes acting together. About 259 kilometers per second come from the evacuation of the local void behind us. About 185 kilometers per second come from the pull of the Virgo cluster, 17 megaparsecs ahead, and about 455 kilometers per second come from a deeper attraction toward the direction of Centaurus and Hydra on scales far larger than our immediate neighborhood. Notice how those numbers do not simply add in a line. They are vectors. They point in different directions across the sky. The void pushes from one side. Virgo pulls from another. The great distant mass pulls from a third. The 631 is what survives after all of them combine. Change any one of them, and the total shifts. This is why a single tidy answer for our galaxy's fate is not available. We are a small mass balanced between a nearby emptiness and several distant crowds. The largest of those crowds sits far beyond Virgo. In the direction of our motion lies a chain of great attractors. There is the Great Attractor, about 150 million light-years away, long known as a gravitational anomaly drawing local galaxies toward it. Beyond it, roughly 600 million light-years away, lies the Shapley concentration. Shapley is one of the richest known collections of galaxy clusters in the nearby universe. It is a genuine mountain of matter, and its gravity reaches across an enormous span of space to tug on structures like ours. For a long time, the story ended there. Our motion was described as a fall toward great masses. The void behind us was one detail in a picture dominated by attraction. Then, the picture gained a second half. In the year 2017, Yehuda Hoffman, Daniel Pomerady, Brent Tully, and Helene Courtois looked at the same flows and asked a different question. They did not only map where the matter is, they mapped where the matter is not. And in doing so, they gave the emptiness a partner in the story. Their result described a broad, underdense region on the far side of the sky from Shapley. They called it the Dipole Repeller. The name captures the geometry precisely. On one side of us sits a vast concentration of galaxies, pulling. On the opposite side sits a vast scarcity of galaxies, effectively pushing. Together they form a dipole, a two-ended arrangement with our galaxy caught in the middle. The pull draws us one way. The relative emptiness lets us drift away from the other. The two effects line up along nearly the same axis. The most striking claim in that work is one of balance. The team found that the Shapley attractor and the Dipole Repeller contribute roughly equally to our 631 km/s march against the background radiation. Half the story is a fall towards something, half is a flight from nothing. For most of the history of this subject, only the first half was visible. The second half was there all along, silent, exerting its influence through absence. It simply had never been mapped. The reach of this flow is difficult to picture. The bulk motion associated with the repeller and attractor extends outward to distances of about 20,000 km/s in redshift. Translated into space that is over 1 billion light-years across, it is close to 1/10 of the radius of the observable universe. Our galaxy is not being nudged by its immediate surroundings alone. It is participating in a coherent river of motion that spans a substantial fraction of everything we can see. There is a caution to place beside these grand figures. The exact position of the Dipole Repeller is far less certain than the fact of it. Some reporting places the mapped structure at roughly 220 megaparsecs from us, near a point high in the northern sky, almost directly opposite Shapley. That figure should be held lightly. It rests on weaker sourcing than the velocity of the local void. The pattern, once again, is familiar. We can feel the push in our motion with confidence. We can point to the region of sky it comes from. Drawing its precise walls remains hard, because there is so little there to draw. The uncertainty did not stop the search from widening. Within weeks of the first announcement, in September of the year 2017, the same approach flagged a second candidate. Researchers described another repelling underdensity, sometimes called the cold spot repeller. If real, it would mean the Dipole Repeller is not unique. It would suggest a landscape dotted with several such emptinesses, each contributing its own quiet push to the flows of galaxies around it. This second repeller carries the lowest confidence of anything in our account. It may be confirmed by better maps. It may dissolve under closer inspection. For now it stands as a hypothesis, honestly labelled. What lifted these ideas from suggestion towards structure was better data, gathered patiently. In the year 2019, Tully's team at the University of Hawaii returned to the problem with a far larger sample. Using the Cosmic Flows Survey, they analysed the motions of roughly 18,000 galaxies. The goal was not another single number. It was a three-dimensional map. They traced the boundary where the local void meets the denser region around the Virgo cluster. The work was published in the Astrophysical Journal on the 22nd of July, 2019. The conclusion tied the threads together. Roughly half of our galaxy's deviation from smooth cosmic expansion, the part beyond the general stretching of space, comes from a specific pair of causes. One is the pull of the Virgo cluster ahead of us. The other is the ongoing expansion and emptying of the local void behind us. Two effects, one attractive and one from evacuation, share the responsibility for a large fraction of our local motion. The emptiness is not a footnote in that budget. It is one of the main entries. Sit with the method for a moment, because it is easy to overlook. To weigh an emptiness, these astronomers did not observe the emptiness directly. They observed the galaxies around it. They measured how thousands of galaxies move. Then they asked what arrangement of matter and absence would produce those exact motions. The void appears in the solution as the shape that must be there for the flows to make sense. It is detected the way a missing weight is detected on a balance. You never see the missing mass. You see everything around it lean. This is why the language of pushing must be handled with care, even now deep into the story. The local void does not shove. The Dipole Repeller does not reach out with a hand. Neither one contains a force generator. What they contain is less than average matter. Everywhere else, ordinary matter pulls. In these regions, that pull is weaker, because there is less to do the pulling. A galaxy caught between a crowded region and an empty one feels the crowd more strongly than the emptiness, so it drifts toward the crowd and away from the void. From inside that motion, it feels exactly like being pushed. The push is real as an effect. It is a shortage of pull dressed as a force. That reframing does nothing to shrink the scale of what is happening. If anything, it enlarges it. Our galaxy's flight from the local void, its lean toward Virgo, its long fall toward Shapley, all arise from the same simple rule applied across 1 billion light years. Matter attracts matter. Where matter thins, the attraction thins with it. From that one rule, mapped carefully across thousands of galaxies, comes the entire architecture of our motion. And the architecture is still shifting, because the void behind us has not stopped its slow, patient emptying. For years, that emptying was only part of the story. The push from the local void was one vector among several. Astronomers could measure it, they could name it, they could even predict its rough size. But they could not yet see the larger shape it belonged to. The figure of 260 kilometers per second was a local reading. It described the edge nearest to us. It did not describe the whole flow. Thousands of galaxies drift together across enormous distances. To understand that river, someone had to map its motion all at once. That is what a small team set out to do in the year 2017. 4 researchers led the work. Yehuda Hoffman studied the problem at the Hebrew University of Jerusalem. Daniel Pomerade worked in France, at a research center near Paris. Brent Tully returned to the question yet again, now at the University of Hawaii. Helen Courtois carried out her part at the University of Lyon. Tully had helped find the local void 30 years before. Now he helped place it inside something far larger. The team had spent years measuring galaxy velocities. They wanted to see the flow as a single object. Their paper appeared in the journal Nature Astronomy. It carried a title that named a new thing. They called it the Dipole Repeller. The word repeller was chosen with care. It described a region that seemed to drive galaxies away, and the word dipole described its role. A dipole has 2 ends. One end pulls, the other end pushes. The team argued that our motion has both. To understand the claim, hold 2 ideas side by side. In one direction lies a great crowd of matter. Astronomers had known about that crowd for decades. Nearer to us sits a dense region often called the Great Attractor. It lies roughly 150 million light years away. Behind it, much farther out, lies a far greater crowd. This is the Shapley concentration. It rests about 600 million light years from us. It is one of the largest gatherings of galaxies in the nearby universe. For a long time, its pull seemed to explain much of our speed. The new work added the missing half. Opposite the Shapley concentration, in almost the exact reverse direction, the maps showed a vast emptiness. Few galaxies filled it. Little matter lay within it, and the surrounding galaxies leaned away from it. The team named that emptiness the Dipole Repeller. In their picture, our galaxy sits between 2 influences. A crowd on one side draws us forward, a void on the other side lets us fall away. The 2 effects point the same way, they add together. This is the same rule the local void obeys, seen on a grander scale. The repeller does not shove anything. It holds no engine and no force. It is simply a place with less than its share of matter. Everywhere around it, ordinary gravity pulls. Inside it, that pull grows faint. A galaxy poised at its edge feels the fuller regions more strongly, so the galaxy drifts toward fullness and away from emptiness. From within, the drift feels like a push from behind. The Dipole Repeller is that feeling, mapped and measured across a much wider sky. The team made a specific and striking claim about balance. The repeller behind us and the Shapley crowd ahead of us contribute in comparable measure. Neither one alone explains our path. Together they account for a large share of our motion relative to the cosmic microwave background. That background is the oldest light in the universe. Our speed against it is 631 kilometers per second. Half of that pull comes from the crowd we are falling toward. Roughly the other half comes from the void we are fleeing. The push and the pull share the work almost evenly, and the flow they describe is not small. The team traced coherent motion across an immense stretch of space. In the language of redshift, that flow reaches out to about 20,000 kilometers per second, translated into distance that is more than 1 billion light years. It is close to 1/10 of the way to the edge of the observable universe. Across that entire span, galaxies move together in a broad current. Our galaxy is one drop within it. The current has a source and a sink. The Shapley concentration is the sink. The Dipole Repeller is the source. Placing the repeller in the sky proved harder than describing its effect. An emptiness is difficult to pin down. You cannot photograph what is barely there. You can only infer its location from the way nearby galaxies bend away. From that bending, astronomers estimate its position. Some maps place the center of the Dipole Repeller very far out, at a distance of roughly 220 megaparsecs. That is a figure to hold loosely. It carries more uncertainty than the nearer measurements. The direction, however, is clearer than the distance. The repeller sits almost exactly opposite the Shapley concentration in our sky. When you look toward the great crowd, the great emptiness lies at your back. That symmetry is the heart of the discovery. Our motion is not the work of a single hand. It is the work of two hands acting in concert. One hand draws, one hand releases. The map that showed both was built the same way the earlier work was built. It rested on the measured velocities of galaxy after galaxy. Each galaxy is a single arrow. Alone, an arrow says little. Together, thousands of arrows reveal a pattern. The team followed those arrows toward their source. They converged on the empty region behind us. Nothing was there to see, yet everything nearby was moving as if fleeing it. There is something humbling in that result. For most of human history, we imagined the sky as a field of bright things. Stars, planets, and glowing clouds filled our attention. The dark spaces between them seemed like mere background. This work inverts that instinct. The emptiness is not background. The emptiness is an actor. The places with the least matter shape the motion of the places with the most. A region that holds almost nothing still helps steer a galaxy the size of ours. It does so quietly, across hundreds of millions of light years, by the simple absence of pull. The Dipole Repeller also reframed the local void's role. The void beside us is real, and its push is real. But it is the near part of a much larger story. The local void is the emptiness we sit against. The Dipole Repeller is a far grander emptiness that helps set the direction of the whole flow. One is our doorstep, the other is a distant shore. Both push in the same sense, because both are regions of shortage. The near void explains the local reading. The far repeller explains the sweep of 1 billion light years. Tully had a hand in finding each. The thread from the year 1987 runs straight to the year 2017. It is worth pausing on how strange this confidence would once have seemed. To claim that a specific unseen emptiness, far beyond any galaxy we can name individually, is steering us, is a bold thing to assert. Yet the claim did not come from imagination. It came from arithmetic performed on real velocities. The team could point to where the arrows led. They could show that the pattern held. They could estimate how much of our speed each side supplied. That is the discipline of the work. It turns a void, a thing defined by absence, into a measured presence in our equations. The picture was not declared finished. Voids are hard to bound, and their edges blur into the regions around them. Even as the Dipole Repeller was announced, the researchers were candid about its limits. The distance remained uncertain, the exact shape stayed rough, and there were hints that the sky held more than one such emptiness. The same method that had revealed one repeller could, in principle, reveal others. A single void behind us might not be the whole account. The flow across 1 billion light years is complex. More than one region of shortage might contribute to its shape. Within the same year, that suspicion found a target. Researchers using the same approach flagged a second candidate. It lay in a different part of the sky. It appeared to repel galaxies in its own right, on a smaller scale than the dipole itself. This second feature was more tentative. It should be held with even greater caution than the first. But its very possibility carried a lesson. The universe may steer us with several empty hands, not one. The local void, the Dipole Repeller, and any further voids like it would then be members of one family. Each is a place where matter thinned. Each lets nearby galaxies slip away, and each adds its small vote to the direction our galaxy travels. So the story widened again. It began as a single strange number measured near home. It grew into a 3-part accounting of our motion. Then it opened onto a flow spanning 1/10 of the visible universe, driven by a pull and a push of nearly equal strength. And even that grand picture came with a warning attached. The maps were still coarse. The emptinesses were still being counted. The team behind the Dipole Repeller had not closed the question. They had only shown how much larger it was than anyone had thought. The next advance did not come from a larger mirror. It came from a larger count. To feel a void, you must measure motion. And to measure motion, you must measure distance. So the work returned to its oldest and hardest task. Astronomers needed the true distances of thousands of galaxies, not their positions on the sky alone, their real depth in space. That depth is what turns a flat photograph into a map of a current. By the year 2019, that catalogue had grown enormous. Tully and his colleagues drew on a survey named Cosmic Flows. It gathered the measured motions of roughly 18,000 galaxies. Each galaxy was a small marker dropped into a slow river. Each carried a velocity that mixed two separate things. Part of its motion was the smooth expansion of the universe. Part was a peculiar drift shaped by gravity. Separating those two parts was the entire problem. The expansion is orderly and predictable. The drift is the fingerprint of everything unseen. The team published its new map on the 22nd of July 2019. It was not a picture of light, it was a picture of movement. They had taken the velocities of those 18,000 galaxies and reconstructed the flow around us. The result was a 3-dimensional chart of where matter gathered and where it thinned, and near the middle of that chart lay the boundary we had been chasing. It was the edge where the local void meets the denser country around the Virgo cluster. For the first time, that frontier had a shape you could turn in your hands. The new map made the accounting cleaner. It confirmed that our motion is not the work of a single cause. Roughly half of the local group's departure from smooth expansion came from 2 nearby influences acting together. One was the steady pull of the Virgo cluster, drawing us inward. The other was the local void itself, emptying behind us and letting us drift away. Together they explained about half of the more than 600 kilometers per second by which we stray from a quiet cosmos. The rest belonged to structures far beyond, the deeper concentrations of mass we have already named. There was something quietly unsettling in that word. Emptying. The local void is not a fixed hollow carved once and left alone. It is a process still underway. It is a region growing lonelier as time passes. The few galaxies that remain within it are not staying. They are leaving. They fall slowly toward the crowded walls that surround them. And as they leave, the void they abandon grows a little wider and a little more bare. This is not a special fate. It is the ordinary behavior of the cosmic web. In the standard picture of how structure forms, matter migrates from the empty places to the full ones. Overdense regions grow denser as they gather what falls in. Underdense regions grow emptier as their contents drain away. The universe sharpens its own contrasts over billions of years. The bright filaments brighten. The dark hollows darken. The local void is simply one of those hollows, seen from the inside, in the act of becoming more itself. That ongoing drainage is exactly what a simple model predicts. Recall the theoretical rule from the early work. A round void in an otherwise even universe pushes matter outward at about 16 kilometers per second for every megaparsec of its radius. The larger the emptiness, the faster its edges recede. A void spanning at least 45 megaparsecs across should drive an outflow near the value we measure. The observed 260 kilometers per second sits comfortably inside that expectation. The theory and the sky agree, at least in their broad strokes. But agreement in broad strokes is not the same as a solved problem. The size of the local void remains genuinely uncertain. The original measurement placed its core near 45 megaparsecs across, about 150 million light-years. Yet that figure was described as a floor, not a ceiling. To the degree the region is not truly empty, it must in fact be larger. Later reporting stretched the estimate much further. Some descriptions place the broader underdense region somewhere between 150 and 300 megaparsecs across, once the faint surrounding lowlands are included. The difference is not small. It is the difference between a nearby pond and a shallow sea. Why is a mere size so hard to pin down? The trouble lies in what a void is made of, which is almost nothing. You cannot survey an emptiness by counting its stars. There are too few stars to count. You map it instead by its edges and by its effects. You watch the galaxies at its rim and read their motion. You infer the shape of the hollow from the way the current bends around it. It is like charting a lake at night by listening to the streams that feed and drain it. The center gives you no light to work with. It gives you only silence and a pull you must reason your way toward. The wispy filaments that cross the void make the task harder still. The region is not one clean bubble. It is divided by faint bridges of galaxies into a near sector, a northern sector, and a southern sector. Those thin threads are the last inhabitants of a thinning land. They are also landmarks. Each filament is a place where the emptiness is interrupted, and each interruption tells the mapmaker something about the true border. To trace them, you must measure galaxies so dim and so isolated that earlier surveys passed over them entirely. Every fresh distance added to the catalogue tightens the outline by a little. There is a strange comfort in how ordinary all of this turns out to be. The number that opened this story sounded like an accusation. Something empty was shoving our galaxy across space at 260 kilometers per second. But the deeper we followed it, the gentler the mechanism became. Nothing reaches out from the void. Nothing presses on us. We are simply falling, as everything falls, toward the places where matter has collected. The void is not an engine, it is an absence that we happen to be leaving behind. The menace was never in the emptiness. It was only in our first misreading of it. And yet the trajectory itself is real, whatever we call its cause. Our galaxy is not drifting at random. It is carried in a definite direction, at a definite speed, as part of a definite flow. The local sheet moves as one broad raft, its member galaxies sharing the same tilt of motion. We ride away from the local void and toward the crowded regions beyond Virgo. That heading is held across every study, from the first measurement of the discontinuity to the three-dimensional map of the flow. The details shift, the direction does not. It is worth pausing on what that steadiness means for the far future. The void behind us will keep widening. The galaxies that share our sheet will keep drifting toward the denser structures ahead. Over spans of time far longer than any human record, the emptiness at our back will grow into an even greater gulf. Our neighborhood will find itself pressed ever closer to the walls of the cosmic web, while the hollow we came from opens into something vaster and darker. we will not feel it. No instrument aboard our world would register the drift in a lifetime, or in 10,000 lifetimes. But the direction is set, and the current does not tire. There is a deeper question folded inside that slow departure. If underdense regions steer galaxies, and if there may be more than one repelling emptiness at work, then our motion is a sum we have not finished computing. The local void accounts for one clear vector. The larger repeller, mapped in 2017, accounts for another on a grander scale. And the tentative second feature hinted that the family of empty pushers might be larger yet. Each addition is a small correction to the arrow that describes where we are going. The arrow is firm in its broad aim. Its precise length and angle are still being refined, galaxy by galaxy, survey by survey. This is the honest state of the science. We know that we move. We know how fast, to within a narrow margin. We know, in rough proportion, how much of that motion belongs to the pull of clusters, and how much to the emptying of voids. We can name the Virgo cluster and the local void, and assign each its share. We can point, with real confidence, at the direction of the great flow. What we cannot yet do is draw the boundaries of the emptiness with a fine and settled line. The core and the outer reaches of the local void still float between competing figures. The exact geography of the deeper repellers is still coarse. The map is drawn in confident strokes and uncertain edges at once. That mixture of certainty and doubt is not a failure. It is the texture of a living measurement. Each new census of galaxies sharpens the picture without finishing it. The distance to the void center, known only as a lower bound of some 23 megaparsecs, may firm up as fainter galaxies are pinned in place. The width of the emptiness may settle as its filaments are traced to their ends. The share each structure contributes to our motion may be reweighed as the flow field grows more detailed. None of these revisions would overturn the story. Each would only bring it into clearer focus, the way a slow exposure gradually reveals a shape that was there all along. So the void keeps emptying, and we keep leaving, and the astronomers keep counting. The number that began as a single strange velocity has become a doorway. Behind it lies a moving universe, sorted by gravity into the crowded and the barren, with our galaxy set gently adrift between them. We have measured the push and found it to be a fall. We have measured the fall and found it to be part of something enormous. And the mapping of that enormous thing, the great sorting of matter that carries us all, has only just begun to take its true shape. Consider how far that sorting reaches. The motion is not a local twitch. It is a coordinated drift shared by galaxies across an enormous span. When Yehuda Hoffman and his colleagues traced the flow in 2017, they followed it outward through redshift space. It did not fade after a few million light years. It reached to roughly 20,000 kilometers per second in redshift. That figure is a distance written as a velocity. Converted into ordinary length, it spans more than 1 billion light years. That is close to 1/10 the radius of the observable universe. Our small drift is one thread in a weave that wide. Hold that scale for a moment. A single number began this story. 260 kilometers per second, measured near a boundary 7 megaparsecs away. It looked at first like a quiet local fact, but the same physics that pushes us from the local void repeats across that billion light-year span. Whole populations of galaxies lean the same way. They drain from the empty places, they gather toward the crowded ones. The push we feel is one small expression of a flow that dwarfs it. Now, weigh the two ends of that flow against each other. On one side sits the Dipole Repeller, the vast underdensity behind our motion. On the other sits the Shapley concentration, the densest gathering of galaxies known nearby. The two lie on nearly opposite sides of the sky. One pulls, one fails to pull, and the paper that named the repeller reported something striking about their strengths. The push and the pull contribute in roughly equal measure to our 631 kilometers per second. Neither dominates the other. The emptiness behind us matters as much as the wealth ahead. The distances involved are humbling. The Great Attractor, long known as a nearby mass concentration, lies about 150 million light-years away. The Shapley concentration lies far beyond it, near 600 million light-years off. It sits in roughly the direction opposite the repeller. The repeller itself, as later mapping placed it, sits around 220 megaparsecs from us. That figure is drawn from a single catalogue and should be held loosely. It marks a low-density basin near the coordinates 22 hours 30 minutes and 37 degrees. Directly across the sky from it lies Shapley. We ride the long axis between them. There is a subtlety worth pausing on. Most of a galaxy's redshift comes from the plane expansion of the universe. That part tells us little about local structure. It is the smooth stretching of space, the same in every direction. What astronomers hunt for is the small remainder. It is the extra motion left over once the expansion is subtracted. This remainder is called the peculiar velocity. It is the true signal of gravity pulling on matter. Our 631 kilometers per second is a peculiar velocity. It is measured against the rest frame set by the microwave background. In that ancient light, our motion registers as a dipole across the whole sky. Detecting an absence is harder than detecting a presence. A bright cluster announces itself in any survey. An emptiness announces nothing. This is why the local void waited so long to be found. Tully and Fisher named it in 1987, but naming it was only the start. You cannot photograph a hollow directly. You infer it from what is missing, and from how the galaxies around its edge behave. The void reveals itself through motion more than through light. We know it is there because of how firmly it pushes. The Dipole Repeller was not the last emptiness to be proposed. Within the same year, using the same method, the researchers flagged a second repelling underdensity. It was called the cold spot repeller. This identification carries less certainty than the first. It should be treated as a promising lead rather than a settled fact. Yet its very proposal tells us something real. The technique that revealed one hidden void can reveal others. The map of what pushes us may hold more than a single blank region. None of this arrived without labour. Behind every clean number lies a slow accumulation of measurement. To know how a galaxy moves, astronomers must first know how far away it truly is. Distance is the hardest quantity in this science. A faint smudge of light gives no depth on its own, so teams measure it again and again, by different means, galaxy after galaxy. The Cosmic Flows program was built from exactly this patience. By 2019, Tully and his colleagues had assembled the motions of roughly 18,000 galaxies. From that catalogue they built a three-dimensional map. It showed where the local void meets the denser region around the Virgo cluster. That map sharpened the accounting of our motion. Roughly half of the local group's deviation from smooth expansion comes from two nearby causes acting together. One is the steady pull of the Virgo cluster. The other is the ongoing expansion of the local void itself, the slow emptying that pushes us from behind. The remaining share comes from farther away. It comes from the great flow toward Shapley and beyond. So our velocity is not a single force. It is a sum, layered from the near to the distant. It runs from the Virgo pull at 17 megaparsecs to structures a billion light-years off. Recall how neatly the near components divide. About 259 kilometers per second come from the evacuation of the local void. About 185 come from the pull of Virgo. About 455 come from the larger attraction toward the Centaurus and Hydra direction. Added together, with their directions accounted for, they yield the 631 kilometers per second we measure. Each term is a different structure. Each acts on us at once. Our galaxy answers all of them together, and the nearest cause is not finished with us. The local void is not a fixed hollow, it is a region still emptying. Matter within it continues to fall outward toward the walls that surround it. The theoretical picture is simple in outline. A spherical underdensity drives matter away at about 16 kilometers per second, for every megaparsec of its radius. Feed a radius of more than 45 megaparsecs into that rule. A push near 260 kilometers per second falls out on its own. The model is coarse. The real void is ragged, not a clean sphere, but the arithmetic lands close enough to trust the mechanism. Follow that mechanism forward in time. The void grows because emptiness in an expanding universe is unstable. Slightly underdense regions shed their matter to slightly overdense ones. The gap widens. The empty grow emptier, the dense grow denser. Our galaxy sits on the lit edge of one such widening gap. As the ages pass, the emptiness behind us should stretch further. The push should not switch off. If anything, it should become a more permanent feature of where we are going. We are not passing through the void's influence. We are being carried by it. How far that emptiness truly extends remains unsettled. The original measurement fixed a core at least 45 megaparsecs across. It warned that any departure from true emptiness would only make the void larger. Later reporting, folding in the broader low-density region around that core, has described an extent nearer 150 to 300 megaparsecs. These are not quite contradictions. They are different edges of the same shadow. The dense core of emptiness is one thing. Its faint outskirts are another. Where exactly the void ends and the ordinary cosmic web begins is still being drawn. There is also the matter of our own distance from the center. That figure has a flaw rather than a fixed value. The measurement places us at least 23 megaparsecs from the void's heart, about 75 million light-years out. We sit on its rim, not within it. That is a fortunate seat. From the rim, the outflow is a clean one-directional push. From deep inside, the picture would be more tangled, with emptiness on every side. Our position gives the signal its simplicity. It is part of why the number came out so sharp. So the counting continues. Each new distance measured is one more anchor in the flow field. Each anchor tightens the map, and the map in turn keeps redrawing the balance of forces on our galaxy. What began as one strange velocity has become a program without an obvious end. There is always another galaxy to measure. There is always another filament to trace. There is always another basin of emptiness to weigh against the crowded structures nearby. The story does not close on a final answer. It refines, and with each refinement, our place in the moving universe comes a little more clearly into view. Step back once more, and the shape of the whole becomes visible. We are not adrift in a still sea. We are riding a current sorted by gravity, pushed from a hollow that is still hollowing, pulled toward masses we cannot see with the naked eye. The microwave background holds the record of that motion, written as a faint asymmetry across the sky. The surveys translate that asymmetry into vectors and distances, and behind all of it stands the same quiet fact that opened this account. Something enormous and nearly empty lies beside us, and it is in the gentlest possible sense showing us the door. And yet a door is not a map. To trust the push, astronomers needed to see its edges. A velocity is only a number until you can place it in space. So the work turned from measuring speed toward drawing shape. The question became simple to state and hard to answer. Where exactly does the emptiness end and the crowd begin? That question drove a survey published on the 22nd of July, 2019. The same Hawaii group led by Brent Tully returned to the problem with far more data. This time they gathered the motions of roughly 18,000 galaxies. Each galaxy became a single measured arrow. Each arrow carried a direction and a speed. Alone, one arrow says almost nothing. Together, 18,000 of them begin to trace a landscape. The method rests on a quiet assumption. Galaxies do not choose their paths. They fall according to the gravity around them. Measure how a galaxy moves, and you learn where the mass is and where the mass is not. Streams of galaxies bend away from the empty places. They gather toward the heavy ones. Map enough of those streams and the hidden terrain emerges. The full three-dimensional structure of the local void begins to take form. What the survey drew was a boundary. On one side lay the local void, thin and quiet and nearly starless. On the other side lay the denser region around the Virgo cluster. The Milky Way sits close to that dividing line. We are not deep inside the emptiness, we ride along its rim. And a galaxy on the rim of a void feels two very different neighbours at once. From the void side comes almost nothing. There is little matter there to pull us back. From the crowded side comes a steady tug toward the clusters and the walls. The result is a slow, sustained drift away from the hollow and toward the crowd. The 2019 map put a number on the balance. Roughly half of the local group's deviation from smooth cosmic expansion comes from this pairing. The pull of the Virgo cluster and the ongoing emptying of the local void together account for about half of a motion that exceeds 600 kilometers per second. That figure deserves a moment of care. It does not overturn the earlier work. It confirms and sharpens it. The 2007 measurement had already separated the void's contribution near 260 kilometers per second. The later survey placed that contribution inside a fuller picture, drawn from thousands of galaxies rather than a careful few. The story held. It simply gained resolution. What was once a single strange velocity became a mapped feature of the local universe. Still, the map has soft edges, and honesty requires naming them. A void announces itself by what is missing. You cannot photograph an absence. You infer its size from the galaxies that ring it, and the motions they betray. That inference carries real uncertainty. The original measurement described a core at least 45 megaparsecs across, about 150 million light-years. Later reporting described a broader underdense region, spanning something closer to 150 to 300 megaparsecs, when the surrounding thin zones are included. These figures do not contradict each other. They describe different things. One marks the hollow center, the other marks the wider region where matter simply runs thin. The distance to the void's center carries the same texture. The measurements place that center at least 23 megaparsecs away, roughly 75 million light-years. The word to hold on to there is least. The emptiness could reach farther than the nearest firm bound. As the original study put it plainly, to the degree the void is not truly empty, it must be larger. A perfectly empty region would betray its full size through the motions around it. A region with a few faint galaxies inside hides part of its reach. So the honest statement is a floor, not a ceiling. The local void is at least this wide, at least this distant, and probably more of both. There is a simple physical picture behind the outflow, and it is worth holding beside the maps. Imagine a spherical region emptied of matter within an otherwise even universe. Matter does not sit still at its edge. It drifts outward, away from the hollow and toward the surrounding density. The rate of that drift scales with the size of the void. The theoretical estimate is close to 16 kilometers per second for every megaparsec of void radius. Run that arithmetic on a void more than 45 megaparsecs across, and the outflow lands near the 260 kilometers per second we actually observe. The number we measured, and the number the simple model predicts, sit in quiet agreement. That agreement is part of why the interpretation is trusted. But a model that fits is not the same as a model that is finished. The real local void is not a perfect sphere. It is crossed by wispy filaments of galaxies that divide it into distinct sectors: a near region, a northern region, and a southern region. Those threads are not decoration, they are structure. They break the tidy symmetry of the textbook picture. A real void has lumps and lanes and quiet corridors. The clean 16 kilometers per second estimate is a first approximation of something far more intricate. It captures the scale of the effect. It does not capture every detail of the flow. This is the character of the whole subject. Confident at the center, uncertain at the margins. We can state with real confidence that the local sheet is streaming away from the void near 260 kilometers per second. We can state with confidence that this motion combines with the pull of Virgo near 185 kilometers per second and the larger scale attraction near 455 kilometers per second. Together they build the roughly 631 kilometers per second at which the local group moves against the microwave background. Those numbers rest on decades of measurement and independent confirmation. They are not in serious doubt. What remains open is the shape of the emptiness itself, its exact size, its exact distance, the precise geometry of its filaments, the way it connects to the wider architecture of voids and walls that fills the cosmos. Each new survey narrows those unknowns without closing them, and each answer tends to raise a further question. That is not a weakness of the science. It is how a young field matures. The blurry edge of 2007 became the sharper boundary of 2019. The sharper boundary will in time become sharper still. There is a further reason the void matters beyond its own measurement. It taught astronomers to weigh what is not there. For most of the history of the science, the discipline studied light, stars, galaxies, glowing gas, the bright things that announce themselves across space. The local void forced a different habit. It asked researchers to take absence seriously as a physical actor. An empty region, it turns out, shapes motion just as surely as a heavy one. The map of the universe is not only a map of its lights, it is equally a map of its darknesses, its hollows, its quiet basins where almost nothing lives. That shift changed how the largest structures are understood. The cosmos is not a scatter of galaxies drifting at random. It is a web. Dense filaments and clusters thread through vast empty rooms. Galaxies flow along the threads and drain out of the rooms. The local void is one such room, and it happens to lie against our own doorstep. Studying it up close gives astronomers a rare chance. They can watch in fine detail a process that plays out everywhere across the observable universe. The emptying of the voids, the gathering of the walls, the slow sorting of matter by gravity. And that sorting is not finished. This is where the story leans forward rather than back. The local void is expected to keep growing and keep emptying over cosmic time. The few galaxies that linger within it continue draining toward the denser structures at its edges. As they leave, the hollow deepens. As the hollow deepens, its outward push strengthens. The emptiness is not a fixed feature we happen to sit beside. It is a process still underway, and we are caught inside its early chapters. That raises a question the surveys have only begun to touch. If the void keeps emptying, what happens to our own long trajectory? The motion we measure today is a snapshot of a changing situation. The push of 260 kilometers per second is not a constant carved into the universe. It is the present value of a quantity that has evolved and will keep evolving. The local sheet that carries the Milky Way is not on a settled course. It is riding a current whose strength is still being written by the drift of distant galaxies we can barely see. None of this can yet be forecast with precision. The far future of our galaxy's motion depends on the interplay of many forces. The void behind us and the clusters ahead, the near structures and the ones a billion light years off. Each has been measured with different confidence. Each will be remeasured as instruments improve. The most honest statement is also the most inviting one. We have learned where the push comes from. We have learned roughly how strong it is. We have not yet learned exactly where it is taking us, or how that push will change as the hollow beside us grows quieter still. Consider what it means for a hollow to grow. The local void does not sit still, it drains. The matter inside it does not vanish, it migrates. The few galaxies caught within a void feel the same asymmetry that moves us. They are drawn toward the denser walls that surround them. Over long ages they drift outward toward the filaments and sheets. The interior they leave behind grows emptier than before. That deepening emptiness sharpens the imbalance. The push on everything at the edge grows a little stronger. This is not a special property of our neighborhood. It is how the cosmic web refines itself. Dense regions gather more matter. Empty regions surrender the little they still hold. The universe grows more clumped with time. The hollows grow more hollow. There is a simple relation behind this drift. A spherical void in an otherwise even universe evacuates matter at a steady pace. That pace scales with the size of the void. For every megaparsec of void radius, the outflow grows by about 16 kilometers per second. A hollow tens of megaparsecs wide should push its edges away at hundreds of kilometers per second. Run that arithmetic for an emptiness at least 45 megaparsecs across. The answer lands near the measured value. The 260 kilometers per second we feel is close to what the plane model predicts. That agreement is quietly reassuring. It suggests the picture is not forced. A simple sphere of emptiness, expanding as such a sphere should, reproduces the number we read from the inside. The model is deliberately crude. Real voids are not perfect spheres. The local void is crossed by thin filaments of galaxies. Those wisps divide it into a near sector, a northern sector, and a southern sector. Its true shape is ragged. Its boundaries are soft. So the match between the tidy sphere and the real measurement should not be oversold. It tells us the mechanism is plausible. It does not tell us the void is neat. The honest reading is narrow. An emptiness of roughly this scale, evacuating at roughly this rate, can account for the drift. The finer details remain a work in progress. How do we measure a motion we are part of? We cannot step outside our galaxy and watch it move. We infer the motion from the galaxies around us. Each galaxy has a distance and a velocity. That velocity has two parts. One part is the smooth expansion of the universe, which carries everything apart. The other part is the extra motion left over. It is called the peculiar velocity, the deviation from the smooth flow. Map enough of those deviations and a pattern appears. Galaxies on one side stream one way, galaxies on the other side stream another. From that pattern you can reconstruct the currents that move whole regions. This is the method behind the result. It reads the flow of many galaxies to recover the flow of our own. The most detailed reading of our side of the void came in the summer of 2019. A team led by the same astronomer who first found the emptiness studied the motions of roughly 18,000 galaxies. From those motions they built a three-dimensional map. It traced where the local void gives way to the denser region around the Virgo cluster. The map gave a shape to something long treated as a statistic. It drew the seam between the empty and the full. The study reached a clean conclusion. Roughly half of our galaxy's deviation from smooth expansion comes from two sources working together. One is the pull of the Virgo cluster ahead of us. The other is the ongoing expansion of the local void behind us. Push and pull, counted side by side, explain about half the excess motion. The rest belongs to structures much farther away. Those distant structures are the deeper half of the story. The push of the local void is a local effect. It shapes our motion out to a few tens of megaparsecs. Beyond that lies a larger contest. On one side sits the Shapley concentration, the richest gathering of clusters in our part of the universe. On the other side sits a vast underdensity, the region mapped as the Dipole Repeller. One draws us in, the other lets us drift away. Together they drive a bulk flow that reaches far past our neighborhood. That coherent stream of galaxies extends out to distances measured in tens of thousands of kilometers per second of redshift. In planar terms it spans more than 1 billion light years. That is close to 1/10 of the radius of the observable universe. Our small drift away from the local void is one thread inside a current that wide. The far end of that current is the least certain part. The local void is near enough to chart galaxy by galaxy. The distant repeller is not. Its exact distance and its precise place in the sky rest on coarser reconstructions. The best estimates put the heart of that emptiness a couple hundred megaparsecs away. It lies in a direction almost exactly opposite the Shapley concentration. But those figures carry more doubt than the numbers close to home. The nearer the structure, the firmer the measurement. The push of the local void is among the firmest of all. We sit on its very edge, and an edge is easier to survey than a distant heart. There are hints of more than one such emptiness. Within months of the first map, the same approach flagged a second repelling underdensity elsewhere in the sky. It was given the name the cold spot repeller. The evidence for it is thinner than for the first. It should be held as a suggestion, not a settled fact. Yet it points to something worth keeping in mind. The Dipole Repeller may not be unique. The universe may be threaded with hollows. Each one nudges the galaxies at its rim. Each contributes a small push to the grand tally of cosmic motion. Our own void would then be the nearest example of a common thing. How large the local void truly is remains open. The original measurement described a core at least 45 megaparsecs across. Later reporting has described a broader underdense region several times wider. Some accounts stretch it to well over 100 megaparsecs once its faint outskirts are included. Both descriptions can be true at once. A dense core of emptiness can sit inside a larger, softer shortfall of galaxies. Where one ends and the other begins is a matter of definition. This is why the size figures wander from source to source. They are not contradictions. They are different lines drawn around a shape with no sharp edge. Pinning that edge down is one of the tasks still ahead, and the shape is not fixed. The void will keep emptying. The few galaxies still inside it will keep draining toward the walls. The filaments that cross it will keep thinning with time. As the interior grows barer, the imbalance that moves us grows slightly sharper. The push does not switch off. If anything, it deepens, slowly, across spans of time far longer than any mission. Our galaxy will keep riding the outflow. The clusters ahead will keep reeling it in. The balance between them will shift as the web itself matures. None of this unfolds on a human timescale. It unfolds across billions of years, in the slow rearrangement of the largest structures there are. What we can still do is measure it better. Every one of these numbers rests on distances to galaxies. Sharper distances mean a sharper map. New surveys reach fainter and farther with each passing year. Each one adds galaxies to the flow field. Each one tightens the currents we can reconstruct. The 260 kilometers per second will be refined. The size of the void will be bounded more closely. The distant repeller will be placed with greater confidence, or quietly revised. The value we feel today is not the last word. It is the best current reading of emotion still being traced. The story is not finished being measured. It is being measured still, one galaxy at a time, along the edge of the emptiness we happen to call home. Consider what a single measurement actually holds. A galaxy shows a redshift. Its light is stretched toward the red end of the spectrum. Most of that stretch comes from the expansion of the universe. Space grows, and the light within it grows too. But not all of the shift is expansion. A small part comes from the galaxy's own motion. That part is what astronomers call a peculiar velocity. It is the motion gravity adds on top of the smooth flow. Our own 259 kilometers per second is a motion of exactly this kind. To isolate it, one number is not enough. You also need the galaxy's distance, and that distance must be found without using its redshift. Only then can the two be compared. Expansion predicts a certain redshift for a certain distance. The real galaxy rarely matches that prediction exactly. The gap between the two is the peculiar velocity. It is the fingerprint of gravity pressed onto the smooth expansion. This is why distances matter so much. Without them, the whole flow field collapses into a single blurred number. Now imagine doing this not once but many thousands of times. That is what the mapping surveys attempt. In the 2019 study, roughly 18,000 galaxies were folded into one model. Each galaxy became a small arrow in 3 dimensions. Each arrow pointed the way that galaxy drifts. Alone, one arrow says little. Together they trace the currents of the nearby universe. The arrows converge where matter has gathered. They stream away from the regions that stand empty. Out of thousands of tiny motions, a single flowing landscape appears. In that landscape, our own position becomes legible. The Milky Way sits on the local sheet, along the rim of the local void. Behind us lies the emptiness. Ahead lie the denser structures. The arrows near us lean away from the void and toward the crowd. The 2019 map placed this boundary in 3 dimensions for the first time. It showed where the void's outflow met the pull of the Virgo cluster, and it reached a clean conclusion. Roughly half of our 600 km per second departure from smooth expansion comes from that pairing. The push of the emptying void. The pull of Virgo, some 17 megaparsecs away. 2 causes, 1 shared direction, half the motion between them. The other half reaches further than any single cluster. This is where the wider tug-of-war enters. On one side stands attraction. The Shapley concentration, the densest gathering of galaxies in our part of the cosmos, lies roughly 600 million light-years away. On the other side stands absence. The distant underdensity mapped in 2017 sits in nearly the opposite direction. The 2017 study measured their influence and found something striking. The attractor and the repeller contribute in roughly equal measure. One pulls, one is fled. Their arrows point the same way, and we ride the sum. The scale of that flow is difficult to hold in the mind. The bulk motion mapped in 2017 does not stop at the edge of our neighborhood. It extends outward to distances of some 20,000 kilometers per second in redshift. Translated into space, that is more than 1 billion light-years across. It is close to 1/10 of the radius of the observable universe. Our 259 kilometers per second, the number that names this journey, is one small vector inside that vast coherent drift. The void beside us is a local cause. The full current runs far beyond it. It helps to place the other landmarks along the way. The Great Attractor lies about 150 million light-years from us. The Shapley concentration lies about 600 million light-years off in that direction. The distant repeller, as a mapped structure, has been placed at roughly 220 megaparsecs away. That last position carries less certainty than the others. It rests on sparse data at the far edge of the survey. But the arrangement is clear enough. A great emptiness on one side, a great crowding on the other. Our galaxy caught in the gradient between them. There is a quiet human dimension folded into these maps. The numbers did not arrive from a single desk. The 2017 result joined researchers across the world. The lead author worked in Jerusalem. A collaborator worked outside Paris. Another worked in Hawaii, where much of this mapping has long been centered. Another worked in Lyon. 4 institutions, on 3 continents, tracing one motion. The map of our flight from the void is itself a collaborative object. It is stitched from telescopes and archives that no one nation owns. And yet the honest picture keeps a wide margin. The void's true size is still not fixed. The 2007 measurement bounded its core at no less than 45 megaparsecs across. That is about 150 million light-years of near emptiness. But the authors were careful about the word emptiness. To the degree the void is not truly empty, it must be even larger. Later reporting stretches the broader underdense region further still, toward figures of 150 to 300 megaparsecs. Those larger numbers are softer. They describe a wide low-density zone rather than the measured core. The difference between them is not a rounding error. It is the difference between what has been measured and what remains estimated. The distance to the void's heart carries the same caution. Our position must lie at least 23 megaparsecs from its center. That is around 75 million light-years of thinning space between us and the deepest hollow. At least. The word matters. It is a flaw, not a final value. The center could be further. The emptiness could be deeper. What the measurement fixes is a minimum, and the minimum alone is already vast. Even the mechanism has a simple theoretical anchor. A spherical void in an otherwise even universe does not stay still. It pushes matter outward from its center. In the idealized case, that outflow grows with the void's size. For every megaparsec of the void's radius, The model adds about 16 kilometers per second of expansion. Run that arithmetic on a void of 45 megaparsecs or more. The outflow it predicts lands near the 260 kilometers per second we actually feel. The measured number and the simple model meet. That agreement is not proof, but it is the kind of quiet consistency that makes a strange result believable. So the questions that remain are not small ones. How large is the void, truly, when its faint filaments are counted honestly? How far away is its center? Whether the distant repeller mapped in 2017 stands alone, or shares the sky with others. There are already hints of a second such underdensity, flagged only weeks after the first. Its evidence is thinner, and its status less settled. Each of these questions waits on the same thing: more distances, more galaxies, a sharper flow field drawn from a denser sky. There is also the matter of time. The void is not a finished thing. Structure formation does not stop. Galaxies near the emptiness keep draining toward the denser regions around it. As they leave, the void grows more hollow. As it hollows, its outward push does not fade. If anything, a deeper void presses a little harder on what remains at its rim. Our galaxy sits at that rim, so the 259 kilometers per second is not a fixed inheritance. It is a reading taken during a long, slow emptying. 10 billion years ago the number was different. 10 billion years from now it will be different again. We are watching one frame of a motion that spans the age of the universe. And the frame keeps shifting under the instruments even as they watch, which raises the harder question. Not only how fast we are moving, but where this current is carrying the local sheet next. The direction is not a simple arrow. Our motion is the sum of many pulls and one great push. The emptiness behind us presses outward. The dense regions ahead draw us in. The local sheet travels along the seam where those forces meet. That seam does not point at any single object. It points into the flow itself. Follow the motion outward, and it does not stop at our neighbors. The bulk flow of galaxies around us reaches far beyond the local void. It extends to distances near 20,000 kilometers per second in redshift space. That is more than 1 billion light years. It is close to 1/10 of the way to the edge of everything we can observe. We are not drifting alone. We are one parcel in a current that spans 1/10 of the visible universe. At the far ends of that current sit the push and the pull. The Shapley concentration lies about 600 million light-years away. It is the densest known gathering of galaxies in our region of the cosmos. On the opposite side of the sky lies the Dipole Repeller. It is emptiness where Shapley is abundance. The two act against each other across a vast baseline. One draws the local group forward, the other presses it from behind. Their contributions to our 631 kilometers per second are roughly equal. The nearer void does the same work at a smaller scale. The Great Attractor sits about 150 million light-years away, drawing us on. The local void at our own doorstep pushes in the opposite sense. So the geometry repeats. A push from an emptiness, a pull from a crowd. Our galaxy rides the difference between them. The pattern holds from a few megaparsecs out to hundreds. This is why the 260 kilometers per second is only one term in a longer equation. It is the local push, measured close to home. Beyond it, the Virgo cluster adds its 185 kilometers per second of attraction, from about 17 megaparsecs away. Beyond that, the great pull toward the Centaurus and Hydra direction adds 455 more. Layer them together, and the sum is our full 631 kilometers per second against the microwave background. Each layer belongs to a different scale of the cosmic web. There is a difficulty buried in every one of these numbers. We measure the flow from inside the flow. There is no fixed post to stand on. The local sheet carries our telescopes along with everything else it holds, so astronomers cannot simply watch the current pass. They must reconstruct it from the motions of thousands of other galaxies. Each measured velocity is a clue. The whole map is an inference drawn from the clues together. That is what the cosmic microwave background gives them. It is the oldest light in the universe. It fills the sky almost evenly in every direction. Almost, but not quite. On one side it appears very slightly warmer. On the opposite side it appears very slightly cooler. That faint pattern is a dipole. It is not a feature of the early universe. It is the signature of our own motion through it. We are moving toward the warm side. We are moving away from the cool side. The size of the dipole encodes our speed, so the 631 kilometers per second is not read from a speedometer. It is read from the temperature of the sky, and the challenge is to explain that speed with real structures. That is the task the Dipole Repeller was built to solve. The warm side points toward Shapley and the Great Attractors. The cold side points toward the emptiness. The old maps could account for the pull. They struggled to account for the whole push. The repeller supplied the missing half. Its position is known far less precisely than its influence. The best current estimate places the Dipole Repeller at roughly 220 megaparsecs from the Milky Way. It lies near the sky coordinates of 22 hours 30 minutes in right ascension and about 37 degrees in declination. It sits almost exactly opposite the Shapley concentration on the celestial sphere. These figures carry real uncertainty. A void is defined by what is absent, and absence is hard to pin to a point. The repeller is a region, not a landmark. That uncertainty leaves room for more than one emptiness. Within months of the first result, the same approach flagged a second underdense region. It has been called the cold spot repeller. Its identification rests on thinner evidence than the Dipole Repeller. It should be held as a candidate rather than a confirmed structure. But its very possibility reframes the picture. The sky may not hold one great void that pushes us. It may hold several, layered at different distances, each contributing its own small shove. This is the honest shape of the field. There is a firm core and a soft edge. The firm core is the flow itself. Our speed against the microwave background is measured to within about 20 kilometers per second. The decomposition into a local push, a Virgo pull, and a large-scale attraction is well grounded in the cosmic flows surveys. The soft edge is the geography, the exact size of the local void, the precise location of the Dipole Repeller, the reality of a second repeller. These are drawn in pencil, not ink. The size question is the sharpest of them. The original measurement described a core emptiness at least 45 megaparsecs across. That is roughly 150 million light-years of near-nothing beside us. Later reporting has described a broader underdense zone reaching further still, into the range of a few hundred megaparsecs when the faint surroundings are included. The two figures are not truly in conflict. One counts the hollow center, the other counts the wider, shallow basin around it. But they remind us that a void has no crisp wall. It fades outward into ordinary space. The simple physics still holds across that fading. A spherical emptiness in an otherwise even universe evacuates matter from its interior. The rate scales with the size of the void. About 16 kilometers per second of outflow for every megaparsec of void radius. Feed a 45 megaparsec void into that relation, and the expected push lands close to what we measure. The theory and the observation agree without much strain. That agreement is quiet, but it matters. It means the 260 kilometers per second is not a mystery bolted onto our galaxy. It is what a void of that size should do. So the future of our motion depends on the future of the void. And the void is not finished. Galaxies near its rim continue to drain toward the denser structures around it. As they leave, the emptiness deepens. As it deepens, its outward push does not weaken. A more hollow void presses a little harder on whatever remains at its edge. We remain at that edge. This is the sense in which our speed is a reading in progress. It was smaller in the deep past. It will not stay fixed in the deep future. But a growing push does not mean a runaway galaxy. The local sheet is not being flung into the dark. It is being carried along a flow whose far end is dominated by attraction. The great crowds of galaxies still lie ahead. Over the long reach of cosmic time, gravity gathers matter into ever denser knots and drains it from ever emptier gaps. The void will keep hollowing. The attractors will keep pulling. Our galaxy will keep threading the narrow seam between them, at a speed that shifts slowly across billions of years. What no one can yet draw is the precise arc of that thread. To trace it forward, we would need a sharper flow field than we now possess. That means more galaxies with measured distances. It means a denser sampling of the sky in the direction of the repeller, where the traces are few and faint. The 2007 measurement, the 2017 map, and the 2019 survey of 18,000 galaxies, each added resolution to the same slowly clearing picture. Each was a finer frame of the same long motion. The next frame will come from the next survey, and it will refine the numbers again. There is a deeper humility in all of this. For most of human history, the heavens were the fixed thing. The ground moved and the sky held still. Then the earth was set in motion around the sun. Then the sun was set in motion around the galaxy. Now the galaxy itself is set in motion through a web of pushes and pulls that stretches 1 billion light years. At every step the still point receded, and at this step the still point vanished entirely. There is no rest frame, there is only the flow and our place within it. That leaves the final questions open, and they are worth stating plainly before we draw the threads together. How large is the local void, truly, once its faint outskirts are counted? Where does the Dipole Repeller sit? And is it one region or the nearest of several? And carried by the void behind and the crowds ahead, where exactly is the local sheet bound across the ages still to come?